I don't like to be limited, but we are with network address translation. So how can we allow a lot of users, let's say 1,000 users, access to the internet all at the same time while using a very small number of public IP addresses? Remember earlier we discussed the scarcity of IPv4 addresses? Well, so far we have looked at network address translation and we have not seen an example whereby we can overcome that scarcity. Both examples, static and dynamic, have shown us that we can assign one public IP address to every single private IP address during the translation process. But I'd like to take multiple private IP addresses and piggyback all of them on top of a single public IP address. So how can we do this? We can accomplish this by using port address translation, or PAT. And what PAT does is it adds to the NAT functionality by giving the router the ability now to keep track of all these translations, not just based on the IP addresses, but also port numbers. So for example, let's say we have our user over here at 172.16.1.9 who wants to access the internet. Well, when they send their packet, the source address is in the packet of 172.16.1.9. But if you go up to the transport layer tells you the transport protocol that's being used. Let's say it's TCP. And if you go up to the session layer contains what is known as a socket. The socket is identifying the source IP address and the port number that's being used as well. So it's a combination of IP address and port number. Well, because of this socket, we have this information that can be utilized for the translation process that's going to give us a unique identifier for that device that's sending the packet. So then we can translate, and if we translate based on the IP and port number, then when return traffic comes back, we have a specific mapping for the IP and port number now that can be used to ensure that the translation successfully occurs in reverse so we can get the traffic back to that end user. So if we look here at our configuration now, a lot of it's the same. We have an access control list that's defining the internal private IP addresses in the organization that can be translated. 172.16.1.0 through 172.16.1.255. There's our private range. Our internal interfaces, interface Ethernet 0/0, IP NAT inside. Interface 0/1, IP NAT outside. Now, notice we have our 209.165.201.1 IP address with the /28 subnet mask. So we have a range of addresses here. 16 total addresses, first and last are not usable, and then one being used for our router and one being utilized for the ISP. So let's say .2. Leaving us 12 addresses left over. But in this particular case, we're only going to use one. We're going to piggyback all of these private IP addresses. How many do we have in this range? Well, there's 256 addresses from 0 to 255. Minus 2 can't use the first and last, so 254 addresses. All 254 addresses are going to use the same public IP address with PAT. IP NAT inside source, same. It's the same. Wow, this is getting easy. List. That's referring to the access control list for the private IP addresses in the example, and that is access list 1 right here. There's the relationship. And then after that, we specify the IP address that we want to use as the public address. But in this case, we're saying interface. Interface Ethernet 0/1. That's our outside interface. Interface Ethernet 0/1. Now, wait a second. How many IP addresses does interface Ethernet 0/1 have? It only has one. It only has one, the one that's assigned to it. Every other address just happens to be part of the same subnet. But Ethernet 0/1 just has one IP address. Therefore, overload on that IP address. Overload means turn on PAT. Turn on port address translation. So that way there, every single one of these private IP addresses can use this IP address that is on that interface, what happens to be this one right here. So what would our NAT table look like in this example? Our NAT table, let's refer to a user in our network, 172.16.1.9, going to www.cisco.com as an example. Well, the inside global address is going to be the IP address of who? It's going to be the IP address of the Ethernet 0/1 interface. But there's also going to be a port number attached to that. And it's the port number that was utilized by the PC in the packet that it sent. So let's say the port number, we'll just use a number here, 2000. Okay, that's the port number that's being used as the source of this particular transmission. What is the local address? 172.16.1.9. 2000. There it is right there. And then we're going where? www.cisco.com. So what happens with the other client? Their outside or inside global address, so the address they're being translated to, is going to be the same. Let's say they're using port number 3050. So that's the inside global. Inside local is 172.16.1.10. And they're going to www.cisco.com as well. So here's what happens. We have both PCs sending a packet to www.cisco.com. They're using different port numbers, though. So what happens on the router is the router is going to translate the private IP address of .9 and .10 to the public address, but preserve that port number that's being utilized. So that way there, when we look at the traffic that's being sent from 1.9, it has the source when it leaves the router of 209.165.201.1, port 2000. When that traffic returns from the server, the destination address is 209.165.201.1, port 2000. The router then consults its table and says, well, that has to go to 172.16.1.9 at port 2000. And so then it sends it to 172.16.1.9. And if it's the traffic coming from this router, from this PC, right here, when that traffic returns, the destination address is 209.165.201.1. So it's the same public IP address, but the port number is 3050. So since the port number is 3050, the router looks at that and says, oh, I must translate that to that 172.16.1.10, port number 3050. So that's how PAT works. The router has the ability to keep track of all of this information based on IP address and port number to make sure that the traffic is successfully translated out and translated back in.